today. Thank you for coming out. We have Phillips talking about AI and how it's used in motion picture production.
Thanks for coming out. I gave you the same title as the talk that I gave to IEEE a couple of months ago. We're going to talk a little bit about how AI gets used, but not probably in the way that you think of it already. I want to talk about how the group from my lab, some ways that we're thinking about using it that are a little different than, again, some of the more traditional ways that many of you, again, you would have thought ahead of time. So just so you know who that's me when I was a kid, and that was last month. And I started really early in the computer graphics era, and especially in the commercial use of computer graphics. So I started in the mid 1980s with this little company called Pixar, and we were very Pixar back then. I'm going to tell you some weird stories about Pixar on the way. But the one of the things that was really the thing that I liked, and what's great about this group, we're talking about image synthesis. We're talking about it in a way that is typically physically plausible. Okay, so not so much. There were goals at the time for things to be photorealistic and physically correct, but I'm going to go with the word plausible, and we'll come back to this a little bit later. But the idea of photorealism, it has always been this goal in computer graphics, and it's a weird goal to have for reasons that we could, again, spend tons of time on. There was a whole movement in painting about photorealism. If you need another talk, I got another hour on this. But we can kind of talk, a little bit. The goal here is, plausible imagery. So this is a slide from 1987. Any of you who use Make or Make files, anybody old enough to remember the good old days, now you get to use CMake, which gives you an extra letter, I suppose. This is literally from my VT100 in my office at Pixar for a talk that Pete Doctor and I were going to give, and we were joking, right? It's like, this is going to make everything, just you're going to type make film and you're going to have a movie. And of course, now you can do that. So many years later, but we're not going to talk too much about that. I'm going to show you some stuff at the end. I'm going to talk about how we use it in this other domain. This is what I'm doing now. I spent a couple of years doing, couple of decades doing human vision research. So my background is in cognitive neuroscience. I was an architecture major, turned into a cognitive neuroscientist, and doing a lot of biological vision. So this whole plausibility of vision thing has always been important. And ever since I've been imported here, I've been working on this virtual production thing that we have going down the way here. If there's nothing going on, we can go down and see the stage after we're done. Computers are a handy way for making pictures, but unlike when I got started, they're now a primary way that filmmaking is done. All tomorrow's cameras, the idea that comes, by the way, from anyone recognizes All Tomorrow's Parties. It was a mashup. I was listening to Velvet Underground, and drinking and writing a talk. So it's like, well, All Tomorrow's Party. Yeah, anyway, it's terrible, but I couldn't come up with anything any better to brand it. The whole idea was that we wanted to think about how what cameras are still based on the same especially cinema cameras. They're based very much still on the same, projective geometry, optics, traditional physically optical devices that we've been using for forever. And what we wanted to start to think about a little bit is what you can do beyond the optics, the kind of how we can move beyond just a straight kind of optical image acquisition and start to think about some of the things that computer graphics gave us. I love that it's in a acrylic box. I believe this literal machine just sat under my desk at Pixar, and I could kick it all the time. This was when Pixar started. We made hardware, and we made hardware in the service. Though we were part of ILM, and we made hardware in the service of filmmaking. Francis Coppola and George Lucas wanted to be able to edit. And they basically want to be able to work with film without having to use a moviola. And they want to be able to, basically be able to edit. They wanted to be able to pre-visualize. They want to do all these things that we do here with color correction and what have you. They want to be able to do that on a computer. Back then, it was all very, very pragmatic, physical reels of film. You're cutting things with razor blades. And so George created, and there's a couple of great books on this if you're interested, but he created a project called the Droid Project right after Star Wars. And the whole idea of the Droid Project, there were various pieces of the Droid Project. There was the sound droid, there was the edit droid, and edit droid needed a computer frame buffer that could handle, basically that would have enough memory to handle frames of film. So we had and so it was basically just this large group of different hardware and software projects. Those of you who are music nerds, the part of the edit droid, the sound droid used product from New England Digital called a synclavier, which was one of the first sampling synthesizers of the era. Lucasfilm used synclaviers until they couldn't get parts from New England Digital anymore. So they're basically little parts of the Droid Project that spilled out everywhere. But one piece of it that the kind of the irony is now you can, I guess, I'm sure that Adobe there's some editor product I can run on my wrist now, right? And so all this hardware, all this craziness, has turned into things like Final Cut and these various software products. So before the Pixar, there was this very famous shot called SB19. Anybody? Does that ring a bell with anybody? It'll ring a bell in a minute. SB19 was from Jedi, and the SB19 is basically this shot. Let's see here. So I'll tell you the story and then I'll show it to you really quick. But the shot SB19, SB Space Battle, important to remember. Space Battle, it was basically when all the TIE fighters are coming around the Millennium Falcon. The hardcore, IMDb nerd fanatics among you will point out that there is a TIE fighter that passes through another TIE fighter in a Millennium Falcon. Oh my goodness. The reason is because there are basically 63 spaceships in that shot. Each spaceship has its own mat. There are, for those of you who remember film, there are 170 rolls of film that go into that one shot, optically printed in various packs to make that final shot. 170 rolls of film. I've literally laid hands on them, and it's a stack because it's only about 2 seconds, but it's essentially 63 spaceships all on their own layer, all shot with motion control. Rotoscoping wasn't a thing for this type of work, so the editors, the special effects director who basically put this together had his assistant hand draw a little, magic marker around everything. And this, whoops, okay, so let's go here. There you go. So this is the shot right here. There's where it passes through the Millennium Falcon. That's 170 strips of film, packed one after another. The Pixar was designed to stop that insanity. The Pixar was designed so that we could take each one of those passes, run it through a laser scanner, do all of the matting and everything, and then do the optical printing. That for those of you in the student realm here, that was called optical printing. You would basically expose from back to front each layer of film. As I understand it, it took 10 hours to print. So you could start running it through, and it took, let's see, 4 crews, 3 weeks per crew, 10 months just to shoot it. So, you know, for 2 seconds of the film. So there you go. The Pixar was designed to get rid of that. And so that's how this was done, right? And again, this is one of my favorite terrible pieces of illustration, but the idea of having mats, so you're basically keeping parts of the film from being exposed, exposing various parts in different ways. And one of the things that came out of this was a thing that's, again, if you're a long-suffering user of, say, Photoshop or something, the alpha channel is something that came out of ILM and Pixar at the time. And the idea was, it was just a layer. You have your RGB, but it was an extra layer that let you know where stuff is. And that stuff was literally created by, again, somebody being paid minimum wage to just draw around the various TIE fighters and Falcons there. So the thing that I love so much about that is that it allowed us to do this synthetic kind of thing. And again, the beauty of computer graphics compared to most traditional imaging that you think of is that we work well beyond just dealing with RGB as our intermediate channels of information we're going to use. As a matter of fact, in some things, I'm going to show you something here in a bit that had what we would think of as about 170 channels times 3, because you'd have CMY for each of those. But I'm going to show you something that has 2,200 channels of information in it. And it's why? Because you can, right? Computer graphics, beautiful because we can. You can basically, synthesis is great that way because you can just keep adding stuff until you're, blue in the face. So here's a really creative synthesized image that I whipped up of some spheres, very classic image, which looks, by the way, David, you'll be happy to know, it's calibrated correctly because you can see the shadow. If you can't see the reflection in the shadow, then the monitor it's not calibrated right. So this is exciting. I feel every other place I've given this talk, it's like, let me explain. There's black, dark stuff down there. So, if you work in multispectral imaging, you're used to working with more than RGB, obviously. And we've basically, in the computer graphics rendering universe, you'd be right to suspect that sometimes we don't just use RGB. Sometimes we use a full spectrum. Sometimes we use little pieces of the spectrum. Sometimes we add stuff in that isn't physically possible. And this is the beautiful part of all this. And so an old trick that we used to use, oh, by the way, alpha channel, okay, $1 million idea. Really simple equation, that's called the compositing equation. And it just talks about blending things given that alpha channel. Alpha channel is 1 where there's something, 0 where there's nothing, and somewhere in between where there could be something. All of the renderers that we developed at Pixar back then were designed to give you partial coverage. So if, for example, the edge of one of those spheres cut through a pixel, it would have a partial alpha value. We did a lot of stuff we were just joking about arrival times earlier. We did a lot of Poisson distribution kinds of things to figure out when and where to put stuff. But you can see we can use that alpha channel for compositing. Allows you to put it over anything. It's the other way a thing that came later was this idea of transparency. And it's similar to an alpha channel. You can think about it that way, those of you who use like PNGs and things. But one of the things that we could do that was actually quite impressive that you cannot do with any camera that you can find in the physical universe is you can output intermediate parts of the physics of rendering. So on the left, what you see is the diffuse rendering of those spheres and only the diffuse component of it. All right, so you're not seeing any reflection of the observatory, you're not seeing any light or anything. On the right, you're seeing just the specular information. And again, that's confounded in this image. And if you were to take a real picture, oops, sorry. If you were to take a photograph of three spheres up at the observatory, you can't dissociate those, right? It's made it to the sensor being combined. The diffuse and the specular information was combined. So what we would do all the time is render those things separately, because then, and right, whole legions of software have evolved for working with stuff like this. We could then recombine them after the fact to change the shininess or the diffuseness of something. And so right, you've got the specular only information there, you've got the diffuse information there. I can then make versions of this, right? The one on the left still has both components, and the one on the right still has both components, just not as shiny as the one on the left. It turns out to do that, to re-render that, again in the 80s, to render each one of these frames took 20 minutes to render, you know, tweaking one parameter, being able to do it this way, you could do it on the Pixar image computer in literally milliseconds, because that's just an add and two multiplies. So in terms of efficiency, you could real-time dial the shininess of things that you were rendering. And this is in the 80s. This is before graphics cards. The Pixar was a graphics card. But that's all, that's just two multiplications and an addition. That's it. And so the idea of re-rendering that, billions of multiplies, billions of, operators, this was a very useful way of rendering things. And so Pixar is very non-destructive. You saw the make joke at the beginning. We would invariably render tons of layers of partial parts of the optics, of the actual, physical simulation of the scene, and combine them later. And that way, I give the art directors a lot of flexibility and what have you. Here's 6 channels. There's there's inner object reflection and shadows in the middle, shadow map on the left. This is a normal. This is basically where all of the surface normals, so it gives you geometric information. This is just at the very top, just the base color. Right, and you can literally, if you've ever done this, taken a special effects course, whatever, you can take these things and combine them and get that final image, and it gives you some flexibility. This film that Pixar did, this is the one I was going to tell you about. You can go too far. This has 1,200 channels of data that came out of the renderer. So you gave it one specification, one rendering spec, and you got 1,200 images per frame for rendering. So if you're worried about organizing where did my files go? Well, you got 1,200 of them for each frame here. And the idea, what the art director, the reason they did it this way, this was part of a project at Pixar that was designed to explore, it was technological, it was their kind of skunkworks division. And they were trying to come up with ways to give artists ways to control these things. So if I gave you 1,200 dials, artists in the room, I know Evie, this is like a thing that drives people crazy. I give you 1,200 dials. If you just remember back long enough to when you had to adjust the color on a television set, and you'd turn the color dial up and the brightness would go down, and you'd have to turn the contrast up to get the darkness, right? That's just 3 things that interacted. Imagine 1,200 channels. So the goal here was to try to come up with ways so that the artist could say, I want it a little more crinkly, or I want, this color a little more flat, or a little more. And if you've worked with AI, you'll know that there's a lot of, I'll say, unrealized power in the ability to use words to adjust things with AI. But like when Joel and I were talking about earlier, if you AI generated me and it's like, no, I want him to wear a blue shirt, you could type that all day long and never get. I'll have an aqua shirt. It might not. There might be a blue shirt floating here. I was telling him about the time I asked it. We literally said, I want you to use a longer lens, and it just put a camera in the frame with a big, long, comically large lens in it, right? So the specificity of language is terrible, but knobs are great, right? Sliders are great. We even go so far, guitarists and sound people in the room, right? You've got non-linear adjustments for some of your knobs because of the logarithmic exponential nature of perception. So we're good at making levers and sliders and things. Words, not so good. We not so good words yet. Good. And computer understanding words, not so good. So here are 6 of the 1,200 channels, 5 plus a reference. And this is how they are combined. Oh, wait. This is the node graph for getting the final image out and how they are combined. Now, I can tell you a little bit. Colin sent me this, the student who did this originally. Each one of those green boxes has a slider associated with it that the artist can tweak, right? But this is the underlying beef underneath this thing. And it's insane. Right? There are 1,200 variables. My favorite is this little cluster in the upper left that's just black. It's like, what's going on up there? I don't know. It's, we're back to trying to understand how a radio works by taking it apart. You will not understand it from this. And so, but the idea was that that's 1,200 channels of stuff that you could never physically have. Right? Just to get that. So, what about practical photography? Well, for sure, Ricky teaches a computational photography course. I hope still. Is that still, you still teach that? We need to do that. Yeah, right? Well, because all photography is computational now. That's kind of the joke. If you've got that's, by the way, Noam Chomsky, for those of you, my wife had that commissioned and it is in my garden. If you've got one of these, you've got a thing that'll do, that's got a depth sensor on it, right? So you just make this slightly more complicated technical package that gives you a depth map along with the RGB. Now you got RGBZ. Now you can do clever things like portrait mode and all these other kind of things just by adding an extra sensor to the phone. Okay, that's one. But what if we wanted more channels of information? Well, of course, those of you, oh, I'm sorry, I'm not allowed to show you that. Let's see. So I wasn't allowed to show, I found out I wasn't allowed to show you that because it's a secret. But I did ask AI to generate a sensor package for a drone. And there you go, right? That's what you were seeing. So you could load up a drone with enough stuff, or load up a camera with enough stuff. And God knows we do it in our universe, right? This is a motion picture camera that we use. This one we had strapped a depth sensor on it. Majal talked about you can use LiDAR to autofocus on cinema cameras. You can use ultrasound. There's all kinds of cool little tricks you can use. That box at the top, if any of you remember how the SR-71 navigated, that's a star tracker that does celestial navigation of little tiny IR reflective random dots in the ceiling that poor David had to get up in a cherry picker because he's the only one certified. While it wobbled back and forth, we stuck them on the ceiling. We can figure out where the camera is in 3-dimensional space. That's pretty handy. there's a depth map. This is kind of meta, right? There's the depth map of the camera. But the whole idea is we could keep outfitting the cameras with stuff to do some of these weird things and get more stuff. But is that really necessary? And so what I started to think about and quickly drew before I came down is this problem of this, right? A scene, there's any given scene, right? There's some color properties. Those color properties are caused by illumination, pigment, structure, whatever you call them, the three things we need for to see things, right? But the eventual, spectral information is one thing. There's geometric information. There's even identity information about what is what and who is who. But that's things in the world. When you take a camera, oh, I'm sorry. And by the way, we can generate things with it, right? Computer graphics wise. But when I take a camera, all I get is RGB and maybe Z and maybe, again, if you put enough stuff on it. But if I had more stuff, if I had this stuff that's here in the middle, if I had the causes of the RGB, if I had object identity, if I had geometric information about the object, I could take this actual photograph and do things to it that we would do, like those tricks I showed you that we would do with computer graphics. But we don't have a camera that can give us that stuff. It can give us some of it, but not all of it, right? And so it turns out you can, we can use a little AI. And those of you who've ever, spy plane, and photo stereo, early computer graphics, the way that I worked on the Flight of the Navigator, which is this big chrome ship that flies around. And the way we figured out what its shape was is we took a camera and went click, click, right? And we built it from stereo. You can get depth from stereo images, stereo pairs, and then it was a giant pain in the butt, but we were able to make it that way. Now we've got all these great tools that kind of go beyond that, and this is where we're getting into this. We'll get into this a little bit further, but the whole idea, the nice thing about I know we have engineers and scientists here. The beauty is when you get that nice closed form solution, the beauty of having is to eliminate ambiguity so you can solve the equation without any, the depth, or the surface normal, or the color. That is what we do here. Being a cognitive neuroscience person, one of the things that, and color people can take you further down the road on this too, your brain doesn't necessarily need it all, and the way that it works with it isn't exactly how a CCD, or how an electronic sensor is going to work with it anyway. Part of the profit in Color for Fun and Profit is figuring out which parts of that stuff you need and which parts you do not need, right? And how that stuff maps to your head. Getting a nice analytic solution, knowing the depth, I can just tell you, the human brain could not care about the literal distance between Ricky and I, nor the literal distance between David and I, but it knows that David's further away than Ricky. It knows that you're closer because there's all kinds of very simple things you can use in the world. Look around. One of my favorite old experiments, Mike Macbeth, who's a friend of mine at Arizona, he makes the news a lot because he published a paper on how dogs catch frisbees. But how humans catch baseballs was his first paper when we were both in grad school. And it turns out, those of you who are roboticists and robotically inclined will think, why, of course, we calculate the trajectory of the ball and estimate the landing position and all this. And it turns out that you can behaviorally show that the best outfielder on Earth basically uses the two-dimensional change of the ball on your retina, and that's it, in order to figure out where the ball is. There's no 3D calculation going. You go to null out phenomenon that are happening on your retina. Flies do not see the swatter coming and say, I must evade the swatter. they basically, something comes from this side, makes this wing flap faster, and they fly away from it. That's it, right? So it's not as common. Dogs catching frisbees do the same thing. They try to null the float of the frisbee out in their vision. And you can tell that they do this by tracking them as they run, because if they were estimating where it was going to be, you would take one path. And if you were just trying to null it out, you would take a totally different path. Gabe Diaz worked on this kind of thing. So it turns out that, maybe having a perfectly physically accurate description isn't necessary. And gosh, AI seems to be really good at that, at the perfectly plausible but not necessarily accurate description. And so what we have been playing with in our lab, and I'm sure some of you, again, have played with some of these things. This is just a GUI for it. But it turns out that getting depth, right, which used to require a stereo pair at least of images or a depth sensor, this is from just the RGB image. It was there are several models that can compute depth. You don't need a LiDAR depth sensor to compute depth. You can compute it from an RGB image. Now, it's heuristic. It's not exactly right, but is it good enough? Well, it turns out that if all you want to do is blur an image that's further away, yeah, it's good enough because your brain doesn't care. It's sensitive to some things, but some things it's not. The one on the left from the sensor in the phone, the one on the right from an AI model. Okay, took under, under like a tenth of a second. And it's a pretty good depth estimate. We've been trying to do that in, shape from shading has been a thing in human perception since the 70s. And now we just got a little set of weights that you load into a thing that just give it to you now. Does it tell us anything about how our brain works? No. Does it tell us anything about, does it fail in interesting ways? You bet it does. Is it good enough for what we need to do? Most of the time. This is even more impressive. Those are the surface normal. So we're getting actual three-dimensional geometry from a two-dimensional image. That's yet another problem that is very difficult to crack. And that basically, for those of you not familiar, those are basically, think of anything perpendicular to the surface, put a thumbtack on something and it's facing up when it's on the desk and it's facing you when it's on me. That's what you use to compute shading and illumination from. If we have that, we can literally move the light source around from the original image and unrender the image, right? Again, comes out of a model. Is it exactly correct? No. Is it good enough? It is, depending on what you're going to use it from. This, you guys some of you probably use SAM, right? Segment anything. That's every car, everything out in the universe where basically you don't want it to, you need to identify things, you need to segment them. Well, there's SAM run on the same thing. If I want to change Gnome's shirt, I know what it is. This is a thing called a cryptomat in computer graphics. It just tells you where things are and what their identity is. But that came out of a model. That's something that we used to only be able to get out of a computer graphics renderer. Why? Because it had a complete geometric description of the scene, right? That's how we would get that. It knew what the geometry was, and it would output that. Those 1,200 layers we talked about before, some of them are this exact stuff, but it's because we had the Euclidean description of the scene to begin with, not an RGB picture. So we're able to get this stuff back for free. Now, this is not to say that it is perfect. You'll notice that these were run through a relighting algorithm, and you could provide it with an environment. So on the right, I said a German disco in Berlin. On the left, I said the countryside near Gießen in Germany. And it did you can see lightings coming from slightly different places. His forehead has different illumination here. It, for some reason, figured out that my snare drum that was part of the picture is part of the gnome. It thought that a cord that was laying on the ground is some kind of neon. So it's got global stuff happening, but it's not really what you would want. It didn't really decompose it. It's working on the whole image. It's not identifying pieces of it and saying, oh, I need to light this or not light this. I need to do this if it's made out of this. It's just treating the whole image as a big picture. And that's not good enough. It starts to hallucinate weird things in the image. But to what we're working on, here's this. This is a thing called a driving plate. All right. A driving plate is a classic piece of film used, dates back to earliest days of, put a projector behind you as you're driving through Monte Carlo, right? To think about Dr. No for a minute. Lots of really good. It goes back much further than that even. We can do this kind of thing, but these are really handy though, because they basically give you an environment that you might not ever be. However, everything's baked into that image, right? The illumination is baked into that image. The time of day, where you are, is baked into that image, the environment. In order to relight it, you need some extra stuff. And in order to do that extra stuff, you can do it with, you can basically do it with this incredible red frame that has now shown up. You can do it basically, though, you need surface normals and you need depth. So here's the depth map from that two-dimensional image. There was no depth sensor on the camera. This is extracted naively even. I didn't even tune it. I just said go. And there's the depth information. You want to make the background blurry in this? Very easy to do because you got the depth. Here, with no tuning, are surface normals from that environment. Also, no tuning. I have a tuned version that looks like this, but the green areas are pointing up, just so you know. Blue areas are pointing mainly to the left, red areas are pointing that way. But anyway, that's from AI. There's no extra sensors, there's no extra bits on that. So that diagram I showed you earlier, I think I have one from, this is from Max, my thesis student. He's taking it another step and is using spherical acquisition of the driving plate so that it is not viewpoint relative, right? So if you want to look from the left side of the car, you got it. And then we're running the same code on those. So if you want the sun to come from over here, you can basically do that and look out that side of the car. Is it photometrically perfect? Everyone with me? No. Does your brain care? Usually not, right? Unless it's really freaky, and then it cares. We're trying to find where it cares, right? Which parts of this. That isn't as well defined in the psychophysics. We can do this too. Here's the cryptomat. Say your art director does not like that tree that's over there on the left. Oh, we can get rid of that tree. You want that tree to be blue? Yeah, we can fix that. You want that tree to, my favorite is this kind of accidental Peter Max version that I made. Sorry if you have stroboscopic things. But we were talking about that cloud that shows up there. You want to get rid of that cloud? Yeah, we'll get rid of that cloud for you. I feel like a car dealer. You want racks? What do you need? You need trim. We can, and so this is identifying the pieces of the scene, again, naively, in 3D, from a spherical projection on the fly. So that's the kind of stuff that we're working on. And this came from an earlier part in the talk, and I moved it, and I decided, and I did. Here, the point is, your brain doesn't, this is what I studied as a visual neuroscientist for 20 years. That's a butt, right? That's a bull. They're both by Picasso, so no, don't give me any grief. There's genitals and things. But that's a butt from 4 lines. That's not just a butt, that's a female butt. It did an experiment where you straighten out the line on the right and it turns into a guy butt. Right? But that's 4 lines. So those of you who are information theory fans, I would love to, we can come back and talk about what's basically in that image, and it's nothing. But it's a butt, right? And the same thing with the bull. It's like, no, it's a bull. It's not. This one's a little more codified, right? This one you might need some cognition to understand, but that one, the butt, you don't need. That hung, by the way, in the the house I grew up in lovely Appalachia. My mom found a print of that and framed it and put it above the toilet. So I got to see that every day until I was 18 and moved out of the house when I would go in to pee. That was right there on the back of it. Because you always have pictures of, butts in the toilet. So to give you a quick coda, the stuff that I said that I wouldn't talk as much about is this stuff. But I'm going to talk about it real quick anyway. Since I do have time, right? I got it. Most of you think about using AI and ML, for films very much in this way. And again, it exists and you can use it. I fed in the script to what movie and received this as I asked for a 7-word summary of this film. Citizen K. Yeah. Sled drama overshadows rich man's trust issues. I then fed it back in and said, make me a script based on this 7-word summary. And it created a script. I sent it to Frank, who I almost had to call. Frank's a screenwriter here, and had to call 911 because he was on his back. But it created a script called Sled of Secrets. And it was about a guy and his girlfriend having a winter, they were at a winter getaway, and he had a bunch of secrets. And so, right, the kind of the Japanese, the translation trick, you can do that with AI and get perfectly absurd things. And it has no idea, right? I asked it to extrapolate, middle-aged professor talks about artificial intelligence to imaging scientists and received this. I'm looking pretty good here. Oh, I pointed out former Pixar employee. Yeah, so don't forget this part, okay? It's up to you. I worked on a bunch of, I worked on some Pillsbury Doughboy commercials and we used actual puppets. I have a maquette from one of them up in my office that one of the animators I worked with brought it when he came to visit. That's a actual puppet. Back to the Pixar for a moment. These things were made out of foam rubber. And any of you who've ever experienced like old school foam rubber, it just falls apart after, long enough. And there's a wire armature inside of there. And if you've ever worked in a machine shop, it's like doing machining on this scale, and the people who can do it well, it's amazing. And we all try, everybody's like, yeah, I can make my own armatures. And you end up with just a pile of metal sadness. And splinters and eye surgery because anyway. But what would happen is we would bend him and like a piece of the foam rubber would fall out. And so instead of an alpha channel, we would send those off to a place in San Francisco and they would draw what we called a leprosy mat. And the leprosy mat was where pieces of the foam rubber had fallen out so that another artist could go in later and comp the stuff back in. So you don't need an alpha channel. Sometimes it's leprosy. But I fed in the description of a commercial that I did and got this nightmare fuel. It was Doughboy jumps on a plate of biscuits is what, and because that was like a 3-second version. Yeah, you want me to run that again in case you have any kind of, again, Terrible, terrible nightmares. So this is and Evie could give you lots of stories about, you know, this is a known problem, and people are working on this kind of thing, you know, for coherence and what have you. But it really has no idea what the hell it's doing, right? And the whole goal then is to constrain. You got an infinite space of possibilities, and this text that you have created is trying to constrain this infinitely dimensioned space, and you are not good at it. Despite we're all, you know, we're good writers. We all can communicate, words coming out of mouth, saying hello to you, but we're not talking in a way that constrains the space adequately for something as simple as this. And so will we see this change? Of course we will. I would have never thought that this was even possible a year ago. We'll see it change, but will we see it change in a way that is, you know, is Citizen Kane going to come out of one of these things? I seriously doubt it for, you know, monkeys at typewriter reasons, for one thing. But being an optimist, I want to try to use the stuff that I want to try to use some of the artifacts of these processes, right? So machine learning is awesome for making statistical estimates of things that may or may not be right. And if I could train it, if you, again, imagine, you know, training something that needs to see in a different environment, you would just train it with different wavelengths, right? Or you would train it if you needed something. There are constraints to the way the physical world is. James Gibson, my academic great-grandfather, right, was this. Gibsonianism is this notion that perception takes place in an environment. We are not spectrophotometers, right? Although some of us wish we were. So that isn't even, right, this from today. Cameras don't even do that. And so the idea that, yeah, we can measure a whole bunch of stuff in the world, which is great, but and it comes in very handy if you're making 1 million widgets and you need the widgets to be the same. You need process control. You need to differentiate this from this, right? It comes in very handy, but it doesn't mean that that's the stuff that we're using in order to navigate the world. All of you can safely escape this room with no geometric knowledge of this room. There's a door, it'll be bright, and you can just get the hell out of here. No one's measuring and estimating. You ask a robot to get out of here, and it'll be comical, right? But you know gravity's this way, most of us. Yeah, some of us don't, but every time I fall down, I forget. But, right, you know, gravity's there, lights up there, you know. There's good things you can take advantage of, and our brain adapted to that. Why not, instead of trying to turn these models into these machine learning models into measurement devices, why not turn them into devices that can, you know, effectively approximate what we need to either generate images or parse images, and do it in a way that is humanly comprehensible. So anyway, that's all I got. These are people who give me money, without whom we wouldn't be here. But I appreciate it, and thanks for your time.